In the last lecture, we talked about the various features of stellar spectra. And also, we talked about what are the various types of information that can be obtained from stellar spectra. Okay, now in this lecture, so basically our topic for the last lecture was stellar spectra. Now in this lecture, what we are going to talk about is basically color and temperature. We are going to discuss various features of color and temperature of stars. Now regarding this fact, let me show you this picture. Now what you are seeing on your screen, this thing, as you can see, this is basically a globular cluster where there are many stars. So the first thing to observe is that there are so many stars out there. Good. Something more than that. Can you see colors? Of course you can see. See, some of them are quite reddish, some of them are bluish, some of them are whitish. Now from Wien's law, we do know that color can be assigned to stellar objects or stars, since we have observed that the stellar spectra, they resemble that of a black body. Okay, now let me show you yet another picture. Here, yet another picture. This was taken from Hubble telescope. This picture I took from the internet. Again you can see so many stars. This picture is very fascinating. Look at the numbers, probably seemingly uncountable, and also the various types of colors, even more rich than this previous picture. So many types of colors are there. So as I was saying, you see, Wien's law lets us to relate stellar colors to stellar temperatures. Now we know that blue colors dominate the visible light output of very hot stars, with much additional radiation in the ultraviolet. On the other hand, cool stars emit most of their visible light energy at red wavelengths, with more radiation coming off in the infrared. So you see, the color of a star therefore provides a measure of its intrinsic or true surface temperature. Of course, apart from the effects of reddening by interstellar dust. Now it is important to note that from observations we have seen that the hottest stars have temperature of over 4000 degree Kelvin. Okay, see here, as you can see, the hottest have over temperatures more than 4000 Kelvin, while the coolest have temperatures of about 2000 Kelvin. Here I have shown you some of them based on the star color. Approximate temperatures ranging from here 25,000 Kelvin to 3000 Kelvin. These are some of the examples of the stars. So Spica is a blue colored star having temperature of the order of 25,000 Kelvin. Now, before I move forward, okay, just a second, let me talk about little bit about the color indices. So this is my current topic. So what are they? Now you see, in order to specify the exact color of a star, astronomers, you see, normally they measure a star's apparent brightness through filters, and each of which transmits only the light from a particular narrow band of wavelengths or colors. Now, one commonly used set of filters in astronomy, it measures the stellar brightness at three wavelengths, three different wavelengths: U for ultraviolet, B for blue, and V for visual or yellow. Now these filters, so we have a UBV system. Now these filters, they transmit light near the wavelengths of 360 nanometer. So the wavelength is 360 nanometer, here 420 nanometer, and this case it is 540 nanometer respectively. The brightness measured through each filter is usually expressed in magnitudes. So we are talking about magnitudes here. So we are going back to the basics as well. Now note that the difference between any two of these magnitudes, say that between the blue and the visual, here it will be known as the color index. So we will call this BV color index. Now it is by the agreement between various astronomers, it has been said that the ultraviolet, blue and visual magnitudes of this UBV system are adjusted to give a color index of 0 to a star with surface temperature of about 10,000 Kelvin. So we have a system, and here in this system we are giving this index 0 to a star, and what that is, that star having temperature of around 10,000 Kelvin, and this is the star Vega. Now the BV color index of stars range from, this BV color index, it ranges from minus 0.4 for the bluest of the stars, having temperature of about 40,000 Kelvin, 40,000 Kelvin. While, let me rephrase this in a separate graph. Write this again. So as I was saying, the BV index, it ranges, say, minus 0.4 for bluest stars. Okay, having temperature of around 40,000 Kelvin, to plus 2.0 for the reddest stars. Okay, with temperatures of about 2000 Kelvin. It is interesting to note that for the Sun, the value is around 0.65. So this is the value for our Sun. Okay. Now remember, so why are we using, if you ask me, okay, you are using a color index, again, why are we using a color index if it ultimately implies temperature? The main reason we have to remember is because the brightness of a star through a filter is what astronomers actually measure, and we are always more comfortable when our statements have to do with measurable quantities. Now here you will see I have shown you the response of the three filters. Okay, basically this picture, it shows the transparency of such filters in the visible, blue and ultraviolet portions of the visible spectrum. These transparency functions, the way these functions are there, they are not quite identical. Okay, these transparency functions must be taken into account when comparing observed magnitudes to theoretical value. This is important. In regards to this color magnitudes, there is another very important quantity which is known as volumetric magnitude. Now what it is? You see, the apparent magnitude is a measure of the flux density received from a star within certain wavelength range. It is also useful to have a measure of the total flux. Now we must have that as well, total flux, which what I mean to say is something integrated over all wavelengths. Now the magnitude corresponding to this flux is known as volumetric magnitude. However, we have to understand that it is nearly impossible to make a measurement of the flux over all the wavelengths, entire wavelength range. In most cases, however, the flux dies off rapidly beyond a certain wavelength region. Remember that for the sun, so it slowly dies down. Hence, a limited measurement sometimes provide. Now, if I do a measurement in this region or so, then sometimes it provides an excellent approximation to the volumetric magnitude. The spectrum of many stars peak in visible or sometimes ultraviolet wavelengths, and their luminosity dies off rapidly as we go to higher wavelengths. Okay, sorry, what I mean to say is here you see, so it is dying out in this case as well. Fine. What I want is, I know it is nearly impossible to find and also observe and also measure the entire spectrum of a star. Let me repeat this again. So you see, it is nearly impossible, no, not nearly, basically impossible to observe the entire spectrum of the star, and that's why it is useful to define a magnitude for a particular given portion of the electromagnetic spectrum, right? Now, if we use apparent magnitude based on the radiation in all wavelengths, then this magnitude, the magnitude defined from it, is basically the volumetric magnitude for all wavelengths. This is the one. But note that, why was I saying nearly impossible? The reason is that any device for measuring intensity of light does not respond to all wavelengths in the same way, and so finding the volumetric magnitude for measurements with a particular device is not straightforward. Okay, but what we have done just now, we used the UBV system. So basically what we were doing is, we were basically studying the radiation inside a certain range of wavelengths. So you see, instead of doing volumetric magnitude, we used the UBV system. And this technique, where we study the radiation inside a certain range of wavelengths is known as photometry, where to obtain the flux inside a given photometric band, a filter that is transparent to the radiation found inside this band and opaque to the photons outside of it. So this is, say, U band. So this is how we do the measurements. Now in this UBV system, the light from a star is made to pass through, I have just shown you how the filters look like, through a filters which allow light only in the narrow wavelength bands, and from the measurements of the intensity of light that has passed through these filters, we get magnitudes in the U, B and V cases. It is interesting to note that stellar temperatures can be determined by other methods as well, apart from relying only on magnitude, just as we have shown in the last lecture. We can estimate stellar temperature using the absorption spectra, and so we can determine the amount of radiation that is not detected in the visible range, and thereafter apply a volumetric correction to convert the visual magnitudes to the volumetric magnitudes. You see, the definition of magnitude which we used in the very first class is in fact applicable to the magnitudes of two photometric bands of a star. So we can also define magnitudes for two photometric bands of a single star. Now, if one obtains photometric measurements of two photometric bands for a star, you see the flux ratio of these bands, it can be used to obtain the effective temperature. Let me show you an example. Suppose, let me draw the monochromatic flux. Okay, now this corresponds to 15,000 Kelvin black body, definitely, and this corresponds to 4,000 Kelvin. Okay, now I am not writing the units, it's in arbitrary units, say, and the lambda is say this is 1000 in angstrom, and here it is around 10,000. Now you see, here I have shown you the monochromatic flux as a function of the wavelength for two stars. So what I have shown you is the example. I have shown you an example for two stars. Of course, now you understand what is this. These are the temperatures of the two stars. So one star is approximated by a black body, okay, having 15,000 Kelvin, another one is 4,000 Kelvin. Now let me draw the approximate positions of two photometric filters. Now the approximate positions is around here, say, this is visual and this is, say, ultraviolet. Okay, now so So in this figure, where the flux of a star is approximated by that of a black body with temperature T effective, we have shown you two photometric bands for two black bodies at different temperatures. Now you see, if we do a ratio of FV, say FU by FV, flux in V band by flux in U band, and thus basically what does this mean? This means MV minus MU. Again, this is U, FU by FV, so which means MV minus MU. Now it is, you can see from just these two cases, what can you infer? You can easily infer from these two cases by comparison that FU by FV increases with temperature. See here, FU by FV, as the temperature increases, this ratio increases. Now, since the black body flux is pretty well known, so this value FU by FV is associated to each temperature. Assuming that the theoretical fluxes of stars with various effective temperatures can be calculated by the study of stellar atmospheres, the observed values of two apparent photometric magnitudes can be used in fact to obtain effective temperature. Okay. Now if nothing obstructs the light coming from the stars, say for example interstellar clouds, then this MV minus MU here is independent of the distance to the observer. Typically, however, the presence of interstellar absorption or scattering necessitates certain corrections to be brought to observe photometric magnitudes. But let me not now talk about the corrections. So you see, it is the effective surface temperature T effective which determines where the peak of the spectrum will be, and thereby determines the color of the star. So we thus expect a 1-to-1 correspondence between the BV, I am not showing you, I have talked about basically U and V, but similarly we can also talk about BV and T effective. And let me just show you a graph. Here you see, I have shown you the surface temperature for a star as a function of the color ratio, BV by visual by blue, BV, which I was just talking about. Of course, for stars with similar properties. But if you carefully note this, so basically measuring this flux in visual in each of the photometric bands and assuming that the properties of black body, we can indeed relate a temperature of the black body. So we can get the surface temperature. But there is a problem with the graph. If you note closely, then you will see that the star colors we can indeed calibrate them to temperature, but the sensitivity, we lose the sensitivity above say 12 to 15,000 Kelvin when using the visible light colors. Okay. Now as I was just saying, there is another problem with the colors, and that is the dust. So problem with colors, with color indices. One is loose sensitivity above say 12,000 Kelvin, and another is the dust. This I have already mentioned before, dust between the stars. Now these dust particles are very small and have the property that they scatter this dust, they actually scatter blue light more efficiently than red light, and this is known as interstellar reddening. Which means that most stars appear to be redder than they really are. And also stars of a given luminosity appear fainter than you would calculate given their distance and the inverse square law. So as I was saying before, fortunately there is another way to estimate stellar temperatures, which also turns out to be the answer to a mystery that rose as the first spectra of stars were obtained. And this way is basically the spectral stellar spectral types. Or basically spectral classification. You remember I talked about it probably in the last class. Now, long ago it was realized that stars had dramatically different absorption lines in their spectra. Some had very strong absorption due to hydrogen, some had no absorption due to hydrogen, and some were in between. So, strong H absorption lines, in between H absorption lines, and no hydrogen absorption lines. Now, it was done quite long ago. Now, with no knowledge of the cause for this, stars were classified based on the strength of the hydrogen lines in absorption. So, what we did, we just simply classified the stars based on strength of hydrogen lines in absorption, and the classification was like this: A star has strongest hydrogen lines, then followed by B star, which has the next strongest, and so on. Okay. Now, let me show you an example. Yes, let me show you. Now, this thing I have already shown before, but this one is different. You see, this time I am showing you the spectra corresponding to different stars. So, the A star shows only strong absorption lines due to hydrogen. Now, other spectral lines, these ones, other ones, you see, they show weaker hydrogen lines and also lines from other elements. Also, you see, now I am not talking about the temperature right now, I will talk about it later on. But you see, for these M stars, there are also lines from molecules. Here, M stars. Now what about the solar spectrum? This is our sun, solar spectrum. Now I have already shown you this. Now some more spectrum as well. See here. Here I have shown you O, B, A, F, G, K, M. Different types of stars. Also, you can see the hydrogen lines. Here, these are the hydrogen lines. Now, note that the hydrogen lines are at maximum strength and these are the molecular lines. Also note the difference in shape. The shapes are not the same. Now, we will use Wien's law to interpret the different shape later on. So, if we have to understand what is happening, then you can say that we have to ask, why is this happening? Why do some stars show strong absorption due to hydrogen and others don't? Now, the obvious solution would be to imagine that this is probably due to difference in chemical composition of stars. What I mean to say, the one which has no hydrogen is because a star which doesn't show any hydrogen is probably because it doesn't have any hydrogen at all. But you see, this is wrong. This hypothesis was entirely wrong. This is not correct. Well, we have to understand why. You see, spectra differ from one another because stars are not all made of the same chemical elements. As I was saying, this hypothesis is absolutely wrong. Why? I will tell you the most primary reason. The primary reason is that spectra, they look different because stars have different temperatures and not different chemical composition. So, spectra different due to different temperature. So we rule this out, this part. Now most stars have nearly the same composition as the sun, with only a few exceptions. Hydrogen, for example, is by far the most abundant element in most stars. However, lines of hydrogen are not seen in the spectra of the hottest and the coolest stars. Now we have to explain this. Well, this is also not very hard to understand. Why? Come on. In the atmosphere of the hottest stars, what will happen to hydrogen atom? Hydrogen atoms are completely ionized. What does this mean? This means that the electron and proton are separated. An ionized hydrogen cannot produce absorption lines. Understand? Similarly, you see, in the atmosphere of the coolest stars, the hydrogen atoms have their electrons attached and can switch energy levels to produce lines. However, practically all of the hydrogen atoms are in the lowest energy state, which is unexcited in these stars, and thus they can absorb only those photons which are able to lift an electron from that first energy level to a higher level. Photons with enough energy to do this lie in the ultraviolet part of the electromagnetic spectrum, and there are very few ultraviolet photons in the radiation from a cold star. So what does this mean? This means that if you observe the spectra of very hot and very cold star, so we have just explained, if you observe the spectra of very hot and very cold stars, then the most common element in the star, hydrogen, will show very weak spectral lines, or in fact none at all. And this is not because of the composition. This is not because the star doesn't have hydrogen, but this is because of temperature effect, ionization effect. Now let me again see the same old spectrum which I just showed you before. Remember, I was saying we will interpret this. So you see, the Wien's law, it just tells us that these are the hot stars. The spectrum peaking at low wavelengths. Now moving down the sequence, you see the wavelength of the peak of the spectrum moves redward, this side. So this is increasing wavelength. And here only molecules could be seen. So these are hot stars, these are very cold stars. And you see the strength of the hydrogen line here. So this is where it is very strong. These are the hydrogen lines, these three. These are, so the strength of the hydrogen lines is very weak in very hot and very cold stars. Now given the temperature of a gas, it is possible to calculate the fraction of atoms with electrons in any excitation level using an equation known as Boltzmann equation. And also it is possible to calculate the fraction of atoms in a gas that are ionized at any temperature using an equation known as Saha equation. So, but I will not talk about it here. And in fact, it is the combination of both Boltzmann and Saha equations that will actually give you the accurate determination of stellar temperature from the hydrogen line strength. So using this on hydrogen line strength, we can get accurate temperature information. Now I will discuss about this in next class. Okay, so now let me talk about spectral sequence. Well, temperature effects are by far the most important factor determining spectral types. Now once this was recognized, the sequence that I told you before, the sequence from A, B, C, D, it was actually again reorganized based on temperature this time. And now we have 7 standard spectral types. From the hottest to coldest stars, the 7 spectral classes or spectral types, you can say, or spectral classes, 7 standard spectral types or classes, and from the hottest to coldest, these classes are designated O, B, A, F, G, K, M. In fact, recently astronomers have also added 3 additional classes for even cooler objects, brown dwarfs or so, cooler objects. These 3 classes are L, T and Y. Now each of these spectral classes, each of them here, they are, except possibly for this Y class which is still being designed, each of them are further subdivided into 10 subclasses through the numbers 0 to 9. Thus, B0 is the hottest type of B star and B9 is the coolest type of B star. However, note that B9 is still slightly hotter than A0 star. Now you see the hydrogen lines in the visible part of the spectrum, which are basically Barman lines, they are strongest in stars with intermediate temperatures, not too hot and not too cold, as I mentioned previously as well. Now calculations show that the optimum temperature for producing visible hydrogen lines is about 10,000 Kelvin. And in fact, I will show you in my lecture on Saha equation that our results indeed match when we do calculations using a combination of both Boltzmann and Saha equation. Now at this 10,000 degree Kelvin temperature, an appreciable number of hydrogen atoms are excited to the second energy level. They can then absorb additional photons, rise to still higher levels of excitation, and produce dark absorption line. Similarly, every other chemical element in each of its possible stages of ionization has a characteristic temperature at which it is most effective in producing absorption lines in any particular part of the spectrum. Now, let's take a look at some of the details here of how the spectra of stars change with temperature. I have shown you the absorption lines in stars of different temperatures. This is the spectral class and relative strength of the absorption lines. Now, in the hottest A stars, here, those with temperatures over 28,000 Kelvin, yes, here, hottest O star, not A. Let me talk about this one, say. In the hottest O star, having temperatures of around 28,000 Kelvin, only lines of ionized helium and highly ionized atoms of other elements are conspicuous. Hydrogen lines, on the other hand, they are strongest in A stars with atmospheric temperatures of around 10,000 Kelvin, as I mentioned before. For ionized metals, provide the most conspicuous lines in stars with temperatures from 6,000 to 7,000 here in this zone. Or they are important for the spectral type F. Here they will show the dominant. In the coolest M stars, below having below 3500 Kelvin temperature, the absorption bands of titanium oxide and other molecules are very strong. But you must remember that our sun is basically here. It is a G2 star. Okay. Now, to see how the spectral classification works, let's see. Suppose we have a spectrum in which the hydrogen lines are about half as strong as those seen in the A star, half as strong. So there are only two contenders here, these two contenders, right? Now looking at the lines, two contenders, so what can it be? One can be either a, so you see what I am saying again. What I am saying is that suppose we have a spectrum in which the hydrogen lines are about half here. Hydrogen lines are about half as strong as those seen in the A star. In the A star, it is maximum. Now, about half, it will be either in B star or where? It is in G star. These are the two possibilities. But if the spectrum also contains helium lines, then what? Then of course it is a B star. Whereas if the spectrum contains lines of ionized iron and other metals, then it must be a G star. So this is how spectral classification works. Here you see I have basically summarized the various spectral classes. So O, B, A, F, G, K, M, even L, T and Y. So principal features, the temperatures, these are of course very low temperatures, and some of the examples. So as I was saying, O type of star, blue, neutral and ionized helium ions lines. Say G, sun, it's a yellow star. Temperatures in this 5200 to 6000 range, where we have weaker hydrogen lines, strong ionized calcium lines, strong sodium lines and many lines of ionized and neutral metals are there. Now before I finish, let me show you the spectra of stars with different spectral classes. So these are the spectra for the different stars belonging to different spectral classes. Okay. So what did we have? What did we do in this entire journey? So we understood that indeed both color and spectra classes can be used to estimate the temperature of a star. Spectra are harder to measure because the light has to be bright enough to be spread out into all colors of the rainbow, and detectors must be sensitive enough to respond to individual wavelengths. In order to measure colors, the detectors need only to respond to many wavelengths that pass simultaneously through the colored filters. Remember the UBV system? Yes, which has been chosen, and that is to all the blue light or all the yellow green light. Fine. So to summarize, yes, so this is what we have been doing since our first lecture. So we have been trying to measure the various characteristics of stars. So we tried to measure the surface temperature by determining the color, which is a rough estimate. Better estimate or technique is using the measurement of spectrum, and then we get the idea about the spectral type. What about chemical composition? We can get idea when we determine which lines are present in the spectrum of the star. Similarly, for luminosity, we have to just measure the apparent brightness, and again we have to compensate for distance as well. Remember when I was talking about what are the various informations which can be obtained from stellar spectra, there I talked about how radial velocity and also rotation of the star, we can get this information from the stellar spectra as well. Okay, that's it for today.